Welcome. The purpose of this screencast is to show you how to draw a tangent line, and in specific, a line tangent to a curve. And this will help you address the second purpose of this lab. You should recall that the first purpose was how does time affect position for a ball that's speeding up as it goes down an inclined plane. Okay? And this question was answered very nicely by the graphs you see. The first one, actually both of them, are telling you that position, x, is directly proportional to the square of time. This means that if we let the ball roll down for a second, it goes x distance. If we let the ball roll down the hill for 2 seconds, it's going to go 4 times farther. 3 seconds, 9 times farther. 4 seconds, 16 times farther. So it's giving you a fundamental relationship between position and time. But it sure would be nice to know something about how the velocity is changing as the ball rolls down the inclined plane. Well, we can actually do this with the data we have. So I'm going to insert a new page, go to Page, Add Page, and I'll call this page How Does Time Affect Velocity for a ball rolling down an inclined plane? Question. There we go. And I'm going to put a graph here, insert graph, and I'm going to put our original graph. This is our position time graph, and maybe I'll put a text box here too. Insert text, and I'll say, how does time affect velocity? Did I say that right? Yeah, how does time affect velocity for a ball rolling down an inclined plane? There it is. All right. So I'll make this big. That text is nice and small. Edit text size. Let's make it bigger. So that's nicer. There we go. I can go a little smaller. There. All right. Put this at the top. Let's auto arrange our page. And cool. This text is a little big. I don't want it to. I want my graph to be as big as possible. Okay. And I'm going to do something. I'm just going to let this be. Now, this is going to seem weird, but I just double click on the graph. I'm going to make where it says major tick style grid. I'm going to make that black, and I'm just going to put dotted lines. And this is just essentially adding graph paper. Now, I don't really want to see these pluses. I want to just see my best fit curve. So what I'm going to do is, I don't know if I can do it. I might have to go back to my page 1. I think I do. Yeah. Double click on position, options, and let's make them white. Yeah, that'll work. Now, I wouldn't do this when I'm printing the graphs, like when I'm printing the first page. But for my second page, I'm going to do analyze linear fit. Whoops, that's not what I wanted. Haha, just kidding. Analyze model. And I'm going to put in the same equation I had before. So from page 1, I had 7.2 here. I had 0 here and 0 here. Okay? So that's basically the best fit curve of our data. All right? Then, what I want to do, well, you should print out maybe 6 of these, minimum. You could print out more, but 6 should be enough if you don't make any mistakes. But if it's me, I'm going to print out like 10 of them. Or you could use pencil. I don't mind if you use pencil here. And you could just print out 6, because your mistakes are likely. So what you're going to do now, after you print out your graphs, what I'm going to do is just copy it into another piece of software. And here it is right here. Okay? And you notice I don't see, let me delete some of these other ones. Yeah. So these other ones aren't going to work out. I'll just copy. There we go. So I can just copy this over. There we go. So that's like your 6 pieces of paper. Okay? And if you remember in our first unit, the slope of a position time graph tells you velocity. And position you can't see here because because I made it white and it doesn't contrast very well with the background right now. But this is position, this axis. So I'm going to label it. There we go. Haha, whoops. Position. Oh, I'll just go to black. That's no problem. Okay, and the units should be centimeters. That's what it's looking like. Okay. And I'm going to use one of the tools up here now. Now, you won't have these tools, but you have some other tricks you can use that'll actually help you. So I'm going to make a line. And I'm going to make a line that's, okay, that wasn't what I want. I'm going to make a line that's actually tangent somewhere down here. Let's put that line in. I'll start it over here. It's going to have a, whoops, haha. Try that again. Okay, there we go. And I'm just going to adjust the slope. And in theory, a tangent line is only going to hit the curve in one spot. Now, that's kind of impossible to do. I'm just going to do my best. Okay? And then I'm also going to draw a perpendicular. Okay? You'll see what the perpendicular is for in a little bit. I'm going to move this perpendicular around a little bit there. See, what I'm trying to do is put my perpendicular right in the middle of where the tangent line hits the curve to give myself a good estimate of exactly where the tangent line is tangent to the curve. And I'm going to guess, let's see here, that looks like it's 0.3. So I'll call this 0.3 seconds right there. Okay? And I'm going to choose 2 places on that tangent line. There's a nice one, where I think I'm very close to an intersection in the grid. Now, I'm sort of out of luck here, so I'm not going to hit there, I'm not going to hit there, but I'm going to, well, let's see here. Where's a good spot I could estimate looks like it's about halfway. That looks pretty good. That looks okay. That's definitely more than halfway. It could be halfway. Yeah. You know, actually, yeah. Okay, I'm just going to go with this one. Okay. There we go. And it looks like my change in position between those 2 points is going to be, what, 10 centimeters minus, call it 5 centimeters. So that's about 5 centimeters. And my change in time, going from there over to there, looks like each mark is 0.2. So I'm talking 0.2, 0.4, 0.6, 0.8, 1 second. And so that's 2.4 seconds minus 1.4 seconds. Yeah, that's going to be about 1 second then. So from that spot over, looks like my change in time is 2.4 seconds minus 1.4 seconds. So that's going to equal 1 second. So line 1, slope is going to be change in position divided by change in time. I'm looking at 5 centimeters divided by 1 second. What do you think this means? Well, at that moment in time, 0.3 seconds, so I need a statement here so I can make sense of this. At 0.3 seconds, at that moment in time, the instantaneous velocity, of our ball is 5 centimeters over 1 second. Okay. And you would want to do this 5 more times. I'm thinking that you spread your tangent lines out nicely and spread your calculations out. If you notice, I tried to save a big part of this graph so that I'd have room to do another calculation, okay? And you just do the same thing 5 more times. And how will this help us? Well, you'll have 6 velocities at 6 different times, and you're going to want to spread out your tangent lines. Like you might want one here, you might want a line tangent to the curve there, tangent to the curve there. You know, 1, 2, 3, 4, 5. You're really going to want to spread them out. And so you'll have 6 velocities, 6 instantaneous velocities that occur at 6 different moments in time. And what do you think you'll do with that? It's another graph. And that graph will answer the question of how does time affect velocity. And you should probably add in the word, how does time affect instantaneous velocity of a ball rolling down an inclined plane. And if you're lucky, you'll be able to get an equation, and maybe there'll be a slope and intercept that actually makes sense, that you can understand, and you can say for every second, and you can complete that sentence. And yeah, good luck. Have fun.